Hello everyone. In the last part of this module, parametric regression models, we will discuss polynomial features to extend this concept of linear regression to solve complex nonlinear problems. This will also allow us to explain a very important phenomena in machine learning known as Bias-Variance Tradeoff. And after that, we will conclude this module by discussing regularization techniques, which aim to control the complexity of machine learning models. Regularization is something that is not only applicable to linear and polynomial regression, but also you can apply it to a very wide range of machine learning models. Therefore, it is important to understand why we need to use regularization. Let's start looking at our general workflow for training machine learning models. We start by some transformation of input features. We find some predicted outputs, and then we use a loss or cost function to measure the discrepancy of predictions. And after that, we will use an optimizer to find the optimal weights or parameters for our model. So far, we have discussed linear regression models, meaning that in this data transformation layer, we find a weighted sum or linear combination of inputs. However, as we discussed briefly in Module 2, we can consider more complex data transformations, including polynomial models. And in this case, for example, if you have a scalar x as the input, we can consider x squared, x cubed to a certain degree that we want. And therefore, this allows us to find these higher order interactions between input features. To go to this section, the fifth part of this module, recall that one thing that we can do to extend this linear model to solve more complex problems is to find a data transformation before applying this weighted sum or linear combination. So this is what is this function phi of x. In general, if x is a scalar, it can be, for example, up to some degree, let's call it d. And if we have more than one feature, we showed this previously in module 2, then we have all the polynomials up to a given degree. For example, if we have here x1 and x2, then we can have x1, x1 squared, x2 squared, x1 times x2, etc., depending on the degree of the polynomial. And again, something to remember here is that this degree of the polynomial that we use is a hyperparameter, meaning there is a parameter we set before training or learning the parameters of our regression model. And one thing which is very nice about linear regression and its extension polynomial regression is that even though in this case we are considering these higher order features, is still in terms of these parameters theta that we want to learn, they are linear functions of the elements of theta, right? So because anytime you have this dot product between theta and another vector, so we have this weighted uh, sum or linear combination with elements of theta. So still this is technically a linear regression problem, except for the fact that now we have created new or artificial features using these types of polynomial pre-processing. And we can perform this in a very simple way using polynomial features from scikit-learn pre-processing. So it's a module that we have multiple forms of pre-processing, and one of them is this polynomial features. And we know that we can use pipeline in scikit-learn to put together several steps, meaning different types of data transformation and also an estimator, which is a regressor or classifier in general. And in order to show you how this works, let's consider here a synthetic data set, which means that a problem where we create inputs and outputs given a known model, and then we assume that we do not know this underlying model, and we aim to find these coefficients here. And since we want to talk about polynomial regression, we assume that already this y or our output is a polynomial function of the input feature. and then we add some noise to make this a more interesting problem. So in this case, we create 50 samples from -3 to 3 because this rand is from NumPy's random module, creates number from 0 to 1. If we multiply that by 6, we get 0 to 6. And then subtract by 3, we get -3 to 3. And here exactly the equation that we had before. So we can plot these uh, x and y values. In this case, we use plt.plot, and we use this B for blue color, and this dot shows that we want to use these types of markers, right? So this is our inputs and outputs. Obviously, it is very clear just by looking at this, a linear model is not a good representation of this underlying relationship between x and y. And there needs to be some sort of like curvature here. So, and we know already that the optimal degree of this polynomial is 2. But in order to solve this problem, we can import polynomial features from scikit-learn's preprocessing. We import pipeline. In this case, we focus on the simple linear regression. We do not need to necessarily use gradient descent or stochastic gradient descent. Since we're working with a very simple problem, we create a pipeline where we have polynomial features and this regressor, which is a linear regression model. And in this case, we can create also some testing samples. Like here, our X new or X test before was always usually like 2 inputs. But in this case, we have a bunch of them from -3 to 3. And the reason is that now because we want to plot a nonlinear function, we need more than 2 data points. And when you look at the predicted values for these testing data points to be able to find their corresponding prediction function that we have here. So you can see that this is this quadratic function that we find by applying linear regression to these polynomial features that we applied in the previous step. So in general, you can see that if we know the underlying degree, we can, use that as our hyperparameter for these polynomial features because this needs to be set before the training process and everything is straightforward. But in practice, we do not know. So we get this data, right? And it might be in a higher dimensional space, so we cannot easily visualize these. And we want to know what the optimal degree is. So one approach is trying different degrees. In this for loop, we are considering 3 different values, 40, 2, and 1. We already know that 2 is the best probably choice, and 40 is probably not the best since it's going to give us a function that has a lot of oscillations. It's in the sense that this is a degree 40 polynomial, and this degree 1 is just simply a linear regression model, which is not sufficient. Very similar to before, we define polynomial features and then our standard scalar. So in this case, we also use a processing or pre-processing after applying our polynomial features, and then we apply our linear regression. That's how we construct the pipeline. We do .fit and then .predict. So let's look at the result of this experiment. So we have our data points. As we see, degree 1 is this, linear function here. And this does not really capture the true relationship here. You can see that because you cannot capture this really curvature that we need in our data. And this leads to especially some issues for small values of x in this area of like -3 and larger value of x. So those are the points that we get further and further from the linear model. However, something that is more interesting is that when we have this degree 40 in this specific problem where we have 50 data points, we have a lot of oscillations. And you can see that overall, this model is doing a good job of going through the blue dots here. This is our training data. But in terms of generalization, meaning that if you have a test data point, now if you have a test data point, like let's say somewhere here, it can either be a really good model or it can be really, really bad in the sense that these values, they go below, well below -10. And then we will find residuals that are really high. And this is what is known as the Bias-Variance Tradeoff. So remember, in machine learning, we really care about the generalization performance, meaning that we want to know the true performance on a new unseen test data. And this error in general that we have on the test data can be decomposed into three components. One is bias, which is the error that we introduce by approximating a real world problem, which is possibly complex, using a simplified model. So in general, when we say high bias model, means that we make very strong assumptions about data. For example, we assume that it's linear, whereas it may not be linear. It might be more like quadratic or cubic. And therefore, by making such a strong assumption that the data is linear, when it is not, this creates high bias. And high bias also is associated with underfitting, right? So this red line here exactly shows you the idea behind underfitting, meaning that this model, the red one, is not complex enough to represent this data set that we have here. And then we have another important part of this error, which is the variance. So variance, as you know from statistics, represents the model's sensitivity or variability to small fluctuations in the input that we have. So high variance models are very sensitive to training data variations, and this leads to what we call as overfitting. So the green prediction curve here that we have, this is an example of overfitting. So meaning that we really work hard to fit this model to this data, but it is in a way that is extremely sensitive to any variability in the input. A small change can cause a lot of variability or oscillations in the output. And in general, that's not really good because a lot of real world data sets, they follow some sort of like continuity. So they do not have a lot of variability, like as you can see here. So now we have two kind of like, issues that we have to focus. Underfeeding, which is the red line, and overfeeding, which is the green curve. And then we have something called the right feed, which is like this blue one, right? So, and here it is very trivial because we know that the actual data here was generated using this degree 2 polynomial. And there's another way also to summarize these, and the fact that in general, we can consider something known as model flexibility. So in the case of polynomial regression, you can think of the degree of the polynomial as a way of measuring the complexity, meaning that when the degree is too high, the model is too complex. When the degree is 1, the model is too simple. So that's a measure of complexity. In this case, the error on the training data, not on the test data, on the training data, decreases as we increase complexity. Because in this case, we see this training data, and it's easy as we have more complex models to better and better fit to what we have and what we know. However, the error on the test data or a new unseen data, which was not part of the training data, follows a U-shaped curve as the function of complexity. And what this means is that when we have low flexibility, meaning that the model complexity is low, both training and testing errors are high because of underfitting, right? So the model is not complex enough to capture the trends that we have in the training data. And the same thing obviously happens with test data because we are not even having a model that has been trained sufficiently well. And then when we have moderate or slash sufficient flexibility in our model, then in that case, our training error is small. And also our test error is usually a small too because this model captures the underlying data patterns. However, the part that is very important is that as you increase the flexibility of your machine learning model, for example, the degree of polynomial, the error on the training data will still decrease. However, the test error can go higher and higher as we increase the model complexity. And the reason for this is that as you increase model complexity, the variance on the test data can be extremely high. And since we have to add this bias and variance, so that's the idea behind bias variance decomposition, this means that the test error still goes up. So Again, to recap here what we have, so we have two types of error. We have bias and variance. Bias is high when the model flexibility is low because we cannot capture the underlying patterns and we cannot even find a good model that matches the training data. However, the bias will decrease as we increase the model complexity. So meaning that we find more and more powerful models. However, the problem is that as we have more and more powerful models, then the variance or the variability or the sensitivity to input features can be extremely high, so the variance increases. And if we add these green and orange curves, that's where we get this U-shaped curve, which is known as the generalization or test error. So in practice, you want to make sure that you have your training error, testing error, and make sure that you have the right fit. And this is important because in machine learning, we cannot just say that if we use more complex models, we will get better test results. That is not true, right? So you can easily see here when we have really high levels of complexity, and this is a very general term, but in the case of polynomial, that can be the degree of polynomial, then you can see that the performance on the testing data or the error can be really, really high. And therefore, it's always important to use appropriate techniques such as cross-validation to be able to ensure that we are not suffering from, especially like overfitting. In the case of underfitting, it's easier to recognize in the sense that both training error and test error is high. So it's typically less problematic, but with the overfitting problem, which means that we are in this area, that's usually more challenging because the training error is actually low, but the testing error is high. And that's the idea behind this bias variance trade-off or bias variance decomposition. And one of the ways that you can better control this bus variance trade-off is known as regularization. So what regularization does in simple terms is that we always have a loss function. For example, in the case of regression, we have these residual sum of the squares. And what we can do is to add another term to this loss function, which we call this a penalty term, to discourage excessive complexity. So what does this mean? So this means that there are, for example, ways that we can add to this, residual sum of the squares, some other function c, where c measures the complexity, where it can be as simple as just looking the norm of this vector theta. So what does it mean is that we want to make sure that the norm of the vector theta is as small as possible. Obviously, when you want to minimize this overall loss function, we need to make sure that we minimize both sides. And by reducing values of theta, let's say in a case like theta is completely zero, this means that we are not able to explain any information about y. So that's not ideal. But there's obviously a trade-off, right? If theta is also too large, then also this will be discouraged because we are adding this term which measures the norm or length of this vector theta. And there are different ways to measure norm or length of a vector. So one is known as the L1 norm, which is the sum of the absolute values. And the other one is the L2, or what we call as the Euclidean norm, right? The sum of the squares of the coefficients. And we can also combine these two. So the first one, we use L1 norm, or the sum of the absolute values, is known as L1 regularization or Lasso. The L2 version, where we do L2 norm or the Euclidean norm, that's also called regression. And the combination of the two, because we can technically add another term here, which one is for the L1 and one is for L2, then we can call that elastic net regularization. And you can see that if we control the values of these weights and avoid large weights, then what we do is that we can avoid overfitting to make sure that we are not overly sensitive to small variations in the input, because each of these thetas will be multiplied by some input feature. So if the input feature is, let's say, has a small changes, then it really depends on theta that how much that will translate to the output that we have. And here we have the overall loss function with the penalty term, which is this C theta. Obviously, we need to always use some parameter like lambda, which is another hyperparameter or constant that we have to choose before training our model, which measures the trade-off between fitting this model to this data that we have and also how much we want to penalize large values of theta. And here, for example, we have the formula for L2 regularization, which is the sum of the square of these weights or coefficients. And with the L1 norm, we just have the sum of the absolute values. So we do not take these powers of 2, we just take the absolute values. So if you want to, for example, apply the Reg regression or L2 regression, you can use the Reg model from linear model of scikit-learns. And in this case, what we do is that very similar to before, we generate a synthetic data. In this case, let's say that our data has cubic format, right? So the actual relationship has some x cubed with some coefficients. We add some noise from the standard normal distribution. So this x and y will be our training data, and x new is what we want to use to measure the performance of our model. And in this case, we are considering three different values of alpha. So alpha is exactly this lambda that we use here. So different implementations use different names. And again, that's something that is always important to know what they refer to. So alpha there refers to this regularization strength or regularization parameter lambda. We are considering three values, 0, 10 to the negative 5, and 1,000. So 0 means there's no regularization. 10 to the negative 5, we have just a small amount of regularization. And 1,000 means we have a very strong regularization. And then for different values of alpha, we go through this pipeline and we set this parameter alpha of the Reg regression. We do model fitting, and then we draw our prediction. So that's what we want to look at the end. If we have some test data or new data, what the output looks like. So now if you look at this, you see very interesting results. So these black dots or circles here are training data. You can see that if we don't use any regularization here, we have some variability in the output. And in particular, you can see that this drop in the value because this model is now able with no regularization to change very, very fast. And that's why you can see that just by getting a little bit out of this sort of like last data point that we have here, this function thinks that it has to drop very fast. And this is mainly happening because we don't have any more data points here. So the model can behave whatever it wants to in some sense. And then even when we add a little bit of regularization, like, 10 to the negative 5, you can see that now this green one, the green curve, is much smoother. So this is the idea behind regularization, to be able to control the behavior of the output given small changes in the input space. On the other hand, if you choose alpha to be like, let's say 1000, so this is a very strong regularization, you can see that this mainly enforces these thetas to be very, very close to 0. And therefore, we only get that intercept term with very minimal changes as x increases. So obviously, this red one is not really a good choice because there's so much regularization that we are not even like feeding this model to this data. But you can see that, if you have a small amount of regularization, you can see using this green curve here that we can find much better representation of the output. Now, the other question that you may have is comparing L1 and L2 regularization. And remember, L1 is called Lasso and L2 is Reg regression. To explain this in a very nice, intuitive way, we can use actually this function called make underscore regression function, which is part of scikit-learn. And this is used to create synthetic regression problems. And the nice thing is that in this case, you can consider even more than one feature. So you can create problems in higher dimensional spaces. So in this case, we are creating 50 training data points. We are assuming that we have 5 features, so that uppercase D, which is the number of features, is set to 5. And the other thing we do is we set this parameter and informative to be equal to 2. So what this means is that out of these 5 features, they are not linearly independent. There are correlations between them. And there are only 2 of them that they are informative. So this is very interesting because now we're considering correlations between input features. And that's one thing that we discussed earlier on, that's one of the things that makes these solving regression problems more challenging, because then you do not have a unique combination of these features to give you the outputs. But let's see how that impact L1 and L2 regularization. So obviously we add some noise level. We add these correlations here that we have. So in this case, exactly, I'm saying that we want to have only 2 informative features, and we introduce these correlations by reducing the rank of these metrics. So in this case, you will see that where we use this make regression with all the inputs that I just mentioned. And I can print coefficients. So one of the options here to set this coef equals true to exactly tell me how the data was generated. So in this case, as we mentioned, we have 5 features. So we need to have 5 thetas. And you can see that only 2 of these thetas are non-zero because that's because of this n informative equals 2. And also I reduce this rank of these data metrics to 2 to make sure that we have some correlations between these input features. Next, what I do, I use the Lasso regularization or Lasso regression. That's also part of linear model, both Lasso and Reg. And we do model fitting. And once we're done with this step, so we can look at the coefficients of the true model. So this is something we usually don't know, but now we know because we created synthetic data. We look at the coefficients of the lasso or L1, and then we look at the coefficients of the reg or L2. And we use bar plots to actually put all these coefficients next to each other and see which model performs better. So if you look at the result, it's very interesting. So remember, here we have 5 coefficients for 5 features. And we use like index 0, 1, 2, 3, 4. And we can see that the true coefficients that we have are these like gray ones, the one for feature index 0 and feature index 2, right? So this comes from 0 and 2. So these are, hopefully we can get as close as possible to these. So you can see that with Lasso, it does very well because it actually recognizes the fact that there are only 2 important features here, and that's this feature index 0 and 2. And although we don't get exactly the same numbers for the coefficient values, we are very close. And the more interesting thing is that you see we do not have any blue values for 1, 3, and 4. However, with L2, you can see that the model, it does recognize the fact that 0 and 2 are more important, but it still assigns some non-zero values to 1, 3, and 4. So here is one of the most important differences between Lasso and Reg. In general, Lasso tends to make sure that more coefficients are actually set exactly to 0. And you can see that here, right? So for Lasso, we do not have any coefficient values for 1, 3, and 4, which is very helpful if that's actually the way your data has been generated, meaning that in your original problem, you only had a couple of features that contributed to the outputs, then Lasso can do a much better job in general. However, you see that the reg regression, it does give us smaller coefficient values for 1, 3, and 4, but still we get some non-zero values, which might be difficult to interpret, especially when we talk about explainability of machine learning models.